Okay, well, after we have spent a considerable amount of time learning how to take derivatives, we're now going to, in this module, spend some time learning how to undo derivatives. And where that at first may sound as if this is mathematics for the sake of just be getting more mathematics, it turns out that, as with everything in calculus, there is a physical reality underlying this process, and we're going to see this physical reality definitely in the last example of this presentation already, even though the example, as with similar examples when we just worked on taking derivatives, is still a bit artificial because it has to be a little bit simpler than the full reality of the situations that you'll ultimately encounter in physics or in engineering, for example. So what's the idea for indefinite integrals? The idea, indefinite integrals or antiderivatives, the idea for those things is that uh, to recover a position function from its velocity function, because the velocity is the derivative of the position, we must formally undo derivatives. So in the last example, as well as in the first point on this slide, we are talking about the physical reality behind the whole thing. And in fact, in physics and in kinematics, one of the standard things that you often have to do is you have to take velocity and or acceleration data and recover position functions from that. And that is again quite realistic, for example, for the navigation of spaceborne vessels. You don't have GPS out there, you can't draw maps or anything like that, right? A spaceborne vessel, if you're looking at a probe that goes to another planet, that thing is just in a void. And so what you can do with the onboard computer is you can keep track of what kind of acceleration you went through at what stages, how much fuel was ejected at what velocity to do what kind of change in the velocity function of the object. You can keep track of the gravitational fields of all the celestial bodies that are around that, and from that you can plot the course. So that kind of undoing derivatives, on one hand, it's a good abstract problem to predetermine the course of say, vehicles that are being launched into space, but also then to make adjustments as the vehicle continues to travel. So that means we need to undo derivatives. And simply put, this undoing derivatives is what symbolic integration is about. Integration is also associated with the computation of areas. We will take care of that in separate modules. First, just the area in one module, and then the connection between antiderivatives and areas will be taken care of in the module on the fundamental theorem of calculus. So undoing derivatives, what does that mean? We are given a function, and that function is actually a derivative, so it's f prime, not f, and we're supposed to find the original function f. Symbolic integration then also is a useful reading skill for applied classes, because in a lot of applied texts you're supposed to solve integrals, and the text just goes, here's the integral, here's the solution, and then of course you wonder, well, why is that the integral? And just being on top of some symbolic integration will allow you to read that kind of thing with a lot more confidence and get a better connection to the material that way. So this is similar to actually algebra being a fundamental reading skill for any kind of mathematics-based class. The stronger your algebra is, and I hope it's certainly gotten reinforced nicely through what we've done with differentiation, but the stronger your algebra is, the less you have to worry about it and the easier the rest of the class becomes. The presentation here shows the underlying idea in some simple integrals, and further presentations will then consider more complicated functions where we're pretty much going to verify what a teaching assistant once told me, and that is differentiation is technique, integration actually is art. So let's see, what do we have? The definition is that if you have a function f, then a differentiable function capital F is called an antiderivative of lowercase f if and only if capital F prime is lowercase f. But what we will see right away is there will not just be one antiderivative for a given function. For example, when you have the function f of x equals 2x, then each one of the functions f of x equals x squared, capital F of x equals x squared, capital G of x being x squared plus 3, and capital H of x being x squared minus 9, all three of these functions are antiderivatives of 2x. And how can we check that? Well, we can just take the derivative of each one of them, and the derivative of each one of them is 2x. So double checking will always just be that we take derivatives. But that means now that even though multiple solutions to a problem are not new to us, you've seen that, for example, with the quadratic formula, infinitely many solutions may feel new, because after all, you can add any number here and the derivative of x squared plus any number will be 2x. So we will have infinitely many possible solutions. That may feel a bit new. I think the only place in the early curriculum where you may have seen this for sure is solving systems of linear equations, specifically dependent systems of linear equations. So either way, whether we've seen it or not, whether we like it or not, we need to figure out how bad that ambiguity can be. And there is a theorem that tells us how bad it can be, and that is that if you have a function that is defined on an interval, and the interval is definitely needed, but it's just an abstract hypothesis here, and if f, capital F and capital G are antiderivatives of f, then there is a constant c such that one antiderivative is equal to the other antiderivative plus that constant for all x in the interval I. So we've seen up here that the ambiguity in this example was that we could add constants, and this theorem down here tells us now that really adding arbitrary constants is all that the ambiguity is going to be, which is a bit reassuring then, certainly. So we can define the indefinite integral of a function f, and that's supposed to be the family of all antiderivatives of f, and it's denoted by integral f of x dx, and the reason for this notation will become clear once we've got the fundamental theorem of calculus, but as I said, that will be another module. In this module, we're going to focus specifically on the physical idea of recovering positions from velocity, and we're going to focus on the techniques how to do that. The function f is called the integrand, the variable x is called the integration variable, and if f is defined on an interval and capital F is an antiderivative of f, then the indefinite interval is just given by the antiderivative plus c. So if we can just undo derivatives and then add arbitrary constants, we can find any indefinite integral, and we've got a little bit of vocabulary that every so often you run into when you talk to people about this stuff, namely the integrand and the integration variable. Okay, the constant c is also called the integration constant, so we've got more vocabulary on this panel. And before we actually talk about symbolic antiderivatives, I want us to visualize what this integration, what this antidifferentiation does. And that visualization tool is the direction field. The direction field consists of little line segments of slope f of x that are placed at the point xy. Remember that when we undo a derivative, so when f is actually a derivative, then f just gives us slopes of that function capital F, and so at the point xy, if the function capital F goes through the point xy, then it would have to have slope f of x there. And so if we just place those line segments, then we know roughly how the antiderivative should be shaped. The direction field then can be used to sketch those antiderivatives, and this geometric idea can also be used to devise a numerical method, and to be precise, it's called Euler's method, which is used to solve certain differential equations numerically. If you're interested in that, check out my presentations on differential equations, which you can also find off of my homepage. Within a direction field, we can also visualize then how the ambiguity arises, and that's another reason to present direction fields right here. And so here we go. Sketch the direction field for the function f of x equals x in the window negative 2, 2 cross negative 2, 2. So negative 2, 2 on the x-axis, negative 2, 2 on the y-axis. And we want to use it to sketch the antiderivative of the function f so that capital F of 0 is equal to 0. Now sketching that can take a while. Well, you first set up the axes and then you sketch the direction field. Here's of course where I'm using a computer, and if you've got software to plot direction fields and it's okay for you to use it, ask your teacher about that, but if it's okay for you to use it, for goodness sake, use it. Sketching all those lines by hand takes quite a while. But what does the direction field do? Well, our function is f of x equals x. Well, when x is equal to 0, that means we get horizontal lines, slope 0. As x increases, first of all, for every x we'll have the same slope because the slopes only depend on x, right? And then as x increases, our slopes will get steeper. At 1, we get slope 1 and so on. And as x gets negative, well, we get negative slopes that get steeper and steeper as we're going to the left side. So that's what this looks like, and that sort of already shows us that any kind of function that follows these things, and these are really like velocity vectors in a wind tunnel, or so a particle that would follow these velocities would have to get this kind of a parabolic shape. And if we want to sketch the antiderivative with f of 0 equals 0, physically we would really just put our pencil right here and then go out horizontally and realize that, well, now the slopes are getting more and more positive, and so we would get a sketch that goes up like this. And towards the left, we'd also go out and we'd realize that, yeah, as we're going right to left, we're also going up like this, and we're getting a curve that looks like that. And in fact, well, that's what it is. And of course, I used my computer here to get a better picture than what I could get if I were to use my mouse to draw that, which is quite painful. I've tried that, and I don't have a tablet PC here, which probably wouldn't work for me either because my handwriting is quite terrible. Now let's look at an extension of this problem and simply draw some more antiderivatives. And basically, if we start here, well, we'll get the same kind of parabolic shape because we're essentially following the same kind of directions, right? They're just a little bit higher up, and we do that up here, we get the same shape. We do that up here, we get the same shape. We do it down here, 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 and here. We always get the same shape, and that's the visualization of the integration constant that I mentioned earlier. Basically, your function gives you the direction field determines the shape of the antiderivative, and then the integration constant just pushes that shape up or down. Okay, with that we can now talk about some elementary symbolic antiderivatives. And antidifferentiation formulas are basically differentiation formulas read backwards. So what's the antiderivative of x to the n? Well, the derivative of a power is the same power with the exponent reduced by 1. Well, okay, so if you undo the derivative, you have to add 1 to the exponent, and that's what happened here. But then you have to make sure that when you differentiate this most essential part of the antiderivative, that you actually get back what you got here. And the derivative of x to the n plus 1 is n plus 1 times x to the n. Well, that's not what we have here, so we have to put this additional multiplicative constant 1 over n plus 1 in here. And then, just like I said, to verify an integration, you just take the derivative of the integral, and the derivative of this function really is x to the n, so that works out. And then something that almost becomes a reflex, you typically put the plus c here at the back. And that works for n not equal 1. Well, let me take a pause here. It should work for n not equal negative 1. Okay, we're back. Sorry about the interruption. I'm getting better at catching my typos and fixing them through just a quick recompile. This should be a formula. This is a formula that works for n not equal to negative 1, because of course, if we have a negative 1 here, we would have a 1 over 0, and no matter how much mathematics you know, no matter how sophisticated your tools can get, and I, for example, have done mathematics at a post-calculus level for over 20 years now, I still can't divide by 0, and I never will be able to. Alright, let's move on, and let's hope there aren't any further mistakes. If we can't do this for n equal negative 1, well, then the next thing to take care of course, is n equals negative 1, and we remember that that is 1 over x in the end, and the derivative of the logarithm, of the natural logarithm, is 1 over x, so the integral of x to the negative 1 is ln x plus c. The antiderivative of the exponential function, well, the exponential function always comes back when you differentiate it, so the antiderivative is just e to the x plus the integration constant. The antiderivative of the sine function, well, let's see, the derivative of sine is cosine, the derivative of cosine is negative sine. So if you go backwards, the antiderivative of the sine function is the negative cosine. And that's because when you take the derivative of the negative cosine, you get negative sine of x, and got the integration constant again. The antiderivative of the cosine function is the sine function, right? The derivative of sine is cosine. And then we've got a couple that just basically come from the fact that we can read integration formulas backwards. The antiderivative of 1 over square root 1 minus x squared, that should be the arcsine, the sine inverse, yeah, arcsine x plus c, and that's because this is the derivative of the arcsine. The antiderivative of 1 over 1 plus x squared, well, the derivative of arctangent is 1 over 1 plus x squared, so this is arctangent x plus the integration constant. And the antiderivative of 1 over cosine squared of x, the derivative of the tangent is 1 over cosine squared x, so this should be tangent x plus c. Now the ones that are typically remembered really are 1 through 6. Now that doesn't mean you're guaranteed that you're never going to encounter those. It's just that you might sweat it a little bit more when you encounter those, and that has happened for me too. I can recognize them now because, of course, I've taught this class a couple of times, and I've also taught classes where you encounter that. But yeah, that's these last two are the kinds of formulas that will give you a little bit of a pause because you don't use them that often, but nonetheless, we need them too. There are also some formulas that simply come from how derivatives behave, namely the integral of a sum is just the sum of the integrals. That comes from the fact that the derivative of the sum is the sum of the derivatives. Similar for differences, the integral of a difference is the difference of the integrals. And if you multiply a function with a constant, you can pull the constant out of the integral and get the right result. These are the main rules, and so you can see really at this stage it's nothing but going backwards in differentiation. And so when we do that, we can now work out some examples. For example, we want to compute the integral of 2x cubed minus 3x to the 2/3 plus x to the minus 1. And again, I'm going to put a bunch of steps in here that you probably will not always write out. In fact, will rarely write out, but that way we'll see that every single step is justified. So an integral of a sum slash difference here, first of all, it breaks up into individual integrals. The integral of 2x cubed, where we can also pull out the 2, minus the integral of 3x to the 2/3, where we can also pull out the 3, plus the integral of x to the negative 1. And that becomes 2 times, and here's where we're using this reverse power rule, right? N is 3, so 1 over n plus 1 is 1/4. X to the n plus 1 is x to the 4th, so we get 2 times 1/4 x to the 4th for the first one. That continues here, where of course now when we have to deal with fractions, it gets a little bit uglier. We keep the minus 3. We add 1 to the 2/3 in the exponent. Well, 2/3 plus 1 is 5/3, and 1 over 5/3 is 3/5 times x to the 5/3. So that works out with that reversed power rule. And then here we could be tempted to add 1 to negative 1, and if that happens we get 0, and that's a warning sign because we can't divide by 0. And then hopefully we'll remember, yeah, the antiderivative of x to the negative 1 is the natural logarithm of x, so that's what we should get. Remember to put the plus c in there. That's a standard 1-point deduction on many tests, and it's just a nuisance factor, right? But it's just not right without the plus c. And the last step then is that we can simplify a little bit. Well, 2/4 is 1/2. The x to the 4th stays the same. 3 times 3/5 is 9/5. X to the 5/3 stays the same, and the rest, the ln x plus c, also stays the same. And that is already it for this kind of computation. Now we can do the same thing when functions are given in a slightly fancier symbolic form, where we've got the integral of 2 times the cube root of x plus 5 over root x minus cosine x. And really the first step then, just like in differentiation, is that we want to take this fancy notation and turn it into powers, because even though the powers might not be as pretty, the powers are what we know how to handle. So this becomes the integral of 2x to the 1/3, which is what the cube root is, plus 5x to the negative 1/2, because dividing by a square root, the division gives us the negative sign, and the square root is an exponent 1/2. The minus cosine x, of course, stays the same. And now we pull this apart, and we do this just term by term. We keep the 2. 1/3 plus 1 is 4/3, which is the exponent, and 1 over 4/3 is 3/4. So we end up with this term here. Let's see, negative 1/2 plus 1 is 1/2. So we keep the 5, and 1 over 1/2 is 2. So we get 5 times 2, and the x to the 1/2. That's the exponent that we get from just adding 1 to the original exponent. And the antiderivative of negative cosine x is negative sine of x, because the antiderivative of the cosine is the sine, plus c. And then again, the only thing we can do here is simplify a little bit. Yeah, 3/2 x to the 4/3, 10x to the 1/2, minus sine of x plus c. And if you wish, you could also turn this back into this notation. As you can see here, I wasn't quite sure whether I did that or not. I didn't, and unless it's specified, you might as well leave it in that form, I think. So finally, the promised example that talks about recovering positions from velocity data that I mentioned in the introduction. Well, so here is an admittedly made-up problem. You've got a car moving along a straight road with velocity v of t being 2t cubed plus 5. Now that's a car that's accelerating seriously, because your velocity is going up with the cube of the time. I mean, that's something that cannot be sustained very long. I'm not quite sure how you would sustain it even for short amounts of time, but it is something where we can just do the computations here. So yes, it's made up. We're saying that the position at time t equals 0 is s of 0 equals 3, and that'll tell us a little bit as to how we're using the integration constant. And what we want to know is the position after 4 time units. Let's assume that all the times are measured in seconds here. That way we can talk about times in a more natural thing, in a more natural unit than just time units. Well, the position is the antiderivative of the velocity, so we need to find the integral of 2t to the third plus 5 dt, and after all the uglier stuff we've done in the previous panels, that's not too bad, right? The integral of t cubed is 1/4 t to the fourth times 2 is 1/2 t to the 1/4. The integral of 5, well, the integral of a constant is just a straight line, so the integral of 5 is 5t. And that's because 5 is, if you want to do that with a power rule, 5 is 5 times t to the 0. 0 plus 1 is 1, so you get t to the 1, and the 1 over 1 just is 1, so we don't have to write that down. And we have to, of course, also have the plus c here, so that was simple intentionally, because this problem discloses more about what the integration constant does, because now we know that 3 is the position at time t equals 0, and that has to be equal to whatever we're getting here, and what we're getting here is 1/2 0 to the fourth plus 5 times 0 plus c, which gives us that c is equal to 3. Now, if your function here is not 0 at the point where you have data given, then your integration constant need not be the number that is given here, but in this problem it just happens to work out that way. Either way, the position function is 1/2 t to the fourth plus 5t plus 3. Now we look at the problem one more time, and the actual task was to determine the position at time t equals 4. Well, that would mean we have to find s of 4, which is 1/2 4 to the fourth plus 5 times 4 plus 3. Let's see if I can work that out. 4 to the fourth is 4 squared times 4 squared. 4 squared times 4 squared is 16 times 16, which is 256. 256 divided by 2 is 128. 5 times 4 is 20, so 128 plus 20 is 148, plus 3 is 151. All right, I can still do mental arithmetic. That is reassuring. You know by now that I do this kind of stuff every so often just to also reinforce that, yeah, if we can do something mentally, it's a good exercise to do that. Remember, ultimately what you want to do is you want to get these problems right. And you can be sure that even though I was pretty sure of my arithmetic, I also, as I was making these slides, I'm pretty sure I remember checking this also with a calculator just to be absolutely on the safe side. With that, we've talked about elementary antiderivatives. We've seen geometrically as well as symbolically here what the integration constant can do. From here on out, it's going to become a bit more challenging on a symbolic level because undoing derivatives involves a lot more pattern recognition than computing derivatives, but we'll get to that in the next couple of presentations. I'll see you there.